Lecture 1, Set 7, we will go through System Verilog hierarchical modeling concept, how a big team could design a big set of modules by making just things hierarchical so different people can work on things. The first level would be, to try to go through this in a system design. So we want to know what are the specifications of the system, and then what are the blocks that go in that system. Once we define that, then the macro cells are defined, which is the higher level functionality of the cells, and then we go into the microarchitecture of each of the cells, and then that way we could kind of break down and have a separation of concerns for the design and try to design a much bigger design in a hierarchy. The hierarchy could be both top-down, just as I described, or bottom-up. We may have, these modules like IPs that are previously designed. We want to maybe try to have, an 8-bit comparator and then just plug it in somewhere in the system. And then, we kind of try to put together like a few of these blocks to make a bigger block. For example, a 16-bit comparator from two 8-bit ones, and then kind of go from bottom up as well. The hierarchical design is also telling us that every module or every macro or every micro architecture that is being designed has to be tested and verified. So we design it, we verify it, and if it's not according to the specification, we need to iteratively do this design. And this should be done for both separate unit designs as well as integration verification part. When we design things, typically we first design things, at a system level, and then we go hierarchically to lower levels of abstractions. Like if we first do kind of the synthesis, which gives us a net list, but it's not necessarily like telling us what are the physical gates looking like, and then we go to physical implementation, and every part of this needs to be tested and verified before we go to the next level of abstraction. And of course, if you're designing a custom chip, ultimately the last level is trying to send a functional design to the fabrication facility. And then once it comes back, we're going to test it to see if it's working properly or design. So the circuits are basically just too complex. We need to design subsystems, and then we test them and we compose them to form a system. And for this reason, most of the modern designs are going both ways, the top-down, where we design the rough design and go down, and then bottom up. Once we have the micro blocks, we go down and we go from down up and try to have a bigger system. And we will be going through this design in the course. I'm not going to explain everything, on this one slide, which is basically summarizing a few of the lectures we are going to cover in the class. But as you will see in lecture 4, we will have application-specific or field programmable logic as the options for the physical design. In this class, we will be mostly working with field programmable logic, but we will be covering similar basics for both, that you could use the same knowledge in System Verilog for doing both if you go to industry and do that. In summary, what we've learned in Lecture 1 is how digital systems can be designed by a programming language, but it's not actually just like a software programming language, but it's a programming language that translates things to a physical implementation. We learned about the history of this Verilog and System Verilog hardware description language, and we saw our first design examples with System Verilog. We'll continue with Lecture 2, where we will be covering some of the basics of System Verilog and how this is useful for designing bigger systems.